Hi students, and welcome to this lecture which is based on three-dimensional coordinate geometry. Now this is an extension of the coordinate geometry into a third dimension. In our real life, we live in a 3D world. Not every object can be positioned in the 2-dimension. The 3D coordinate system helps us to align and position objects in the space with respect to a fixed point. Now it is the study of geometry using a 3-dimensional coordinate system and involving the applications of principles of algebra. So in this lecture, we will first try to understand some basic concepts, see the equation of line in 3 dimensions in different forms, learn how to frame the equations of planes, and will study about spheres. So let's begin this lecture. So first of all, let's try to understand the 3-dimensional coordinate system. Now we have studied in depth about the 2-dimensional system in the section coordinate geometry, where we studied straight lines, circle, parabola, hyperbola and ellipse. But those were plane figures that needed just 2-dimensional analysis. But in real sense, we live in a 3-dimensional world. So it becomes very important for us to look at things from the 3-dimensional view. So this entire chapter is based on 3-dimensional analysis. But for that, we have to choose a system. So let's try to understand the 3-dimensional system. It is very much similar to the 2-dimension system, just that we have added one more axis for our reference. Let us say that this is OX, this is OY and this is OZ. These three represent 3 mutually perpendicular lines which are known as the 3 axes. Your O is the point of intersection of these axes. Let us say that P, X, Y, Z is any point in the 3-dimensional space. Here we see that X is the projection of this point on the x-axis, Y is the projection of this point on the y-axis, and Z is the projection of P on the z-axis. So we can write any vector R corresponding to the point P, X, Y, Z as R equal to X times I cap plus Y times J cap plus Z times K cap. Your I cap, J cap and K cap represents unit vectors along the x-axis, y-axis and the z-axis. So every point in space is uniquely specified as point P, which is X, Y, Z. So X represents the X coordinate of the point P, Y represents the Y coordinate of the point P, and Z represents the Z coordinate of the point P. Thus, this way we can represent any point in the space with reference to a fixed point, that is O. Yeah, these 3 lines, that is the x-axis, y-axis and the z-axis, together constitute the rectangular coordinate system. Now distance formula. Now if we have got any 2 points A and B in the space, A with the coordinates as x1, y1, z1 and B with the coordinates x2, y2, z2, then the distance between these 2 points A and B is given by AB equal to under root of x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. Thus, if we have got any 2 points A and B in the space with the coordinates x1, y1 and z1 and x2, y2, z2, then the distance between these 2 points is equal to under root of x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. The next is section formula. This section formula is very much similar to the section formula which we have studied in coordinate geometry. So the first type of division is the internal division. Now if we say that any point R, X, Y, Z divides the line segment between the points P with the coordinates as x1, y1, z1 and Q with the coordinates as x2, y2, z2 in the ratio of m is to n, then the coordinates of point R are given by x equal to mx2 plus nx1 divided by m plus n. Similarly, the y coordinate of R is given by my2 plus ny1 divided by m plus n, and the z coordinate of the point R is given by mz2 plus nz1 divided by m plus n. Similarly, if we have external division, that is the point R divides the line segment joining the points P and Q in the ratio of m is to n externally, then the coordinates of R are given by the x coordinate is equal to mx2 minus nx1 divided by m plus n, the y coordinate is equal to my2 minus ny1 divided by m plus n, and the z coordinate is equal to mz2 minus nz1 divided by m plus n. Thus this is the formula for the internal division and the external division. Now direction cosines and the direction ratio. Now let's first try to understand what do we mean by direction cosine. Now consider these three mutually perpendicular axes, x-axis, y-axis and z-axis. Now if we have any point P, x, y, z in the space, then OP becomes a line segment, and let us say that this line segment OP makes an angle of alpha with the x-axis, angle beta with the y-axis and angle gamma with the z-axis. Then cos of alpha, cos of beta and cos of gamma are known as the direction cosines. Your alpha, beta, gamma are called as the direction angles. So in a sense, these angles alpha, beta and gamma represents the direction of this line segment OP in the space. So once again, if any line segment OP makes an angle of alpha with the x-axis, beta with the y-axis and gamma with the z-axis, then cos of alpha, cos of beta and cos of gamma are known as the direction cosines of this line OP. Your alpha, beta and gamma are called as the direction angles. Now, the direction cosines of the x-axis are 1, 0, 0. This is because the x-axis makes an angle of 0 degree with the x-axis, so cos of 0 degree would be equal to 1. Similarly, the x-axis makes an angle of 90 degree with the y-axis, so cos of 90 would be equal to 0. And the x-axis makes an angle of 90 degree with the z-axis because these two are mutually perpendicular axes, so cos of 90 is again equal to 0. Similarly, if we see the direction cosines of y-axis, then they are 0, 1, 0, and the direction cosines of z-axis are 0, 0, 1. Thus, these are the direction cosines of the x-axis, y-axis and z-axis. Now, we also say the direction cosines to be L, M, N. So, at times, we do not write it as cos alpha, we write it as equal to L, cos beta equal to M and cos gamma equal to N. Thus, L, M and N represents the direction cosines of any line. Now, consider this triangle. Let us say that this is the point P. Now, this line OP makes an angle of alpha with the x-axis. So, R times cos alpha is equal to X. Your R is the magnitude of OP. So, we can say that the magnitude of the vector OP is equal to R. So, R times cos alpha would be equal to X, or we write cos alpha equal to L, and so L is equal to X by R. Similarly, we will have R times cos beta equal to Y, and so M would be equal to Y by R, and R times cos gamma equal to Z, so N is equal to Z by R. Thus, if we add all these terms, L square plus M square plus N square, then that would be equal to X square plus Y square plus Z square divided by R square. So, L square plus M square plus N square is equal to X square plus Y square plus Z square divided by R square. But we also know that X square plus Y square plus Z square is nothing but equal to R square. So, R square by R square is equal to 1, and thus we can say that L square plus M square plus N square is equal to 1. Thus, the sum of the squares of the direction cosines is equal to 1. Now, the next is direction ratios. Just now we have studied about direction cosines. Now let's try to understand what are direction ratios. Now if we say that A, B, C are three numbers that are proportional to the direction cosines L, M, N of a straight line, then A, B, C are called as its direction ratios. They are also called as direction numbers or the direction components. So if we have any three numbers A, B, C and these three numbers are proportional to the direction cosines of any line, then A, B, C are called as the direction ratios. So by definition, L by A would be equal to M by B, and that would be equal to N by C. Let us say that all these are equal to some number K. So L would be equal to A times K, M would be equal to B times K, and N would be equal to C times K. Now we also know that L square plus M square plus N square is equal to 1. So K square into A square plus B square plus C square would be equal to L square plus M square plus N square. And so we also know that this is equal to 1. Thus, K square would be equal to 1 by A square plus B square plus C square. Thus, we get the value of K equal to 1 by under root of A square plus B square plus C square. Now, an important thing to note is there can be infinitely many direction ratios, but the direction cosines remain unique. So, for any straight line, there can be infinite number of direction ratios. because direction ratios are just numbers that are proportional to the direction cosines. So we can have infinitely many direction ratios that are proportional to the direction cosines, but direction cosines remain unique. That is, we can have only one set of direction cosines for any straight line. Let's try to solve an example. If 2, minus 3, 6 be the direction ratios, then the actual direction cosines are. So in this problem, we have been given the direction ratios, and we have to find the actual direction cosines corresponding to these direction ratios. So what we do? Let us say that L, M, N be the direction cosines. So we take direction cosines as L, M, N. Now L would be equal to 2 times k, M would be equal to minus 3 times k, and N would be equal to 6 times k. This is because we know that direction ratios are proportional to direction cosines. Now we also know that L square plus M square plus N square is equal to 1. Substituting these values over here, we get 4 times k square plus 9 times k square plus 36 times k square is equal to 1, or k is equal to 1 by 7. Thus we get the value of k equal to 1 by 7, and so L would be equal to 2 by 7, M would be equal to minus 3 by 7, and N would be equal to 6 by 7. Thus the final direction cosines are 2 by 7, minus 3 by 7, and 6 by 7. So thus we can say that if A, B, C are the direction ratios, then the direction cosines would be A by under root of A square plus B square plus C square, B by under root of A square plus B square plus C square, and C by under root of A square plus B square plus C square. So simply using this formula, we can get the direction cosines given the direction ratios. Now the direction ratios of the line joining the points x1, y1, z1 and x2, y2, z2 is given by x2 minus x1, y2 minus y1 and z2 minus z1. So if we have got any two points with the coordinates as x1, y1, z1 and x2, y2, z2, then the direction ratios of the line joining these 2 points is given by x2 minus x1, y2 minus y1 and z2 minus z1. Also, the projection of a line joining any 2 points x1, y1, z1 and x2, y2, z2 on a line with the direction cosines as L, M and N is equal to x2 minus x1 into L plus y2 minus y1 into M plus z2 minus z1 into N. Thus, if we have got any 2 points x1, y1, z1 and x2, y2, z2, and we want to find out the projection of the line joining these points on any line with direction cosines as L, M, N, and this projection of line is equal to x2 minus x1 times L plus y2 minus y1 times M plus z2 minus z1 times N. If the direction ratios of any vector R are A, B and C, then the vector R is equal to modulus of vector R into A times I cap plus B times J cap plus C times K cap divided by under root of A square plus B square plus C square. So if we have got the direction ratios of any vector R as A, B, C, then R would be equal to modulus of R, that is the magnitude of the vector R, into A times I cap plus B times J cap plus C times K cap divided by under root of A square plus B square plus C square. Now we can also write this as modulus of vector R into A by under root of A square plus B square plus C square times I cap plus B by under root of A square plus B square plus C square times J cap plus C divided by under root of A square plus B square plus C square times K cap. Now we also know that A by under root of A square plus B square is equal to L, so we can write it as L times I cap plus this is M, so M times J cap plus this is N, so this would be equal to N times K cap. And L, M and N are the direction cosines, so we can also write any vector R as equal to the modulus of vector R into L times I cap plus M times J cap plus N times K cap. L, M and N are the direction cosines of this vector R.